Hello everybody, and welcome to the final video on the topic of indices and surds in chapter 1 of the Blue Algebra book. So we've done some lessons on indices, last lesson was on surds. Today is still going to be on surds, and in particular the idea of rationalising the denominator, which we'll talk about. Before any of that though, you might be able to predict what's going to come next. 4 warm-up questions for you to have a go at, please. 1, 2, 3 and 4. Try them first before looking at my solutions. So the best way of learning next to nothing is by just copying down my solutions and not trying to apply yourselves. So try them first and then only check the solutions afterwards. So let's start first of all with talking through how to do question 1a. So question 1a, we're asked to simplify fully root 40 plus root 90. So root 40 and root 90 both have a factor that's a square number. A square number which is a factor of 40 is 4. So we can rewrite 40 as root 4 root 10. In pretty much the same way we can write root 90 as root 9 root 10, because 9 is a factor of 90 and is also in itself a square number. Square root of 4 is 2, so we have 2 root 10, and the square root of 9 is 3. So now we have 2 lots of root 10 plus 3 lots of root 10, which obviously gives us 5 lots of root 10. Part B at the bottom, same idea, we're hunting for factors of each surd that are in themselves square numbers. And so 180, hopefully you can spot, that's got 36 as a factor, and 36 is a square number. So we can call that 36 5. Root 36, root 5. 45 is the same as 9 times 5, so we can rewrite this as root 9, root 5. Meanwhile, on the denominator, 125 has 25 as a factor. 25 is a square number because it's 5 squared. And 25 times 5 gives us 125, so we can split this into 25 and 5. Last, root 80. 80 has 16 as a factor, so we can call this root 16, root 5. And if you have a look at each one of these things here, we now have this all in terms of root 5. So just colour coding so you can see what each thing has become, just in case you couldn't do before. The final thing now is just to simplify this in terms of lots of root 5. And so this numerator, the top, we end up with 6 root 5, because square root of 36 is 6. Square root of 9 is 3. And the bottom, the square root of 25 is 5, and the square root of 5 we just leave as is. And minus the square root of 16, square root of 16 is 4. Then we have root 5. And so on the bottom, 5 root 5 take 4 root 5 is just going to leave us with a root 5. And on the top, 6 lots of root 5 minus 3 lots of root 5 is just 3 lots of root 5. And the final step, the root 5 on the top cancels with root 5 on the bottom, and so we just have an answer of exactly 3 at the end. Question 2. Expand and simplify root 2 minus 3 to plus root 3. I'm hoping you can see this is a difference of 2 squares. This is going to be 2 squared minus root 3 all squared. And so that's going to be 4 minus 3, which is actually just 1. For part B, you need to expand out this, so you might want to rewrite it if you want to as the same bracket multiplied by itself twice. This is optional, you don't have to do it this way. But essentially all that's going to happen is the first term is going to be multiplied by itself, so we have 2 squared, which is 4. We then take the product of these 2 terms and double it, so 2 times root 3 is 2 root 3, and we can double that to get 4 root 3. And finally, we square the last thing, so root 3 squared is root 3 multiplied by root 3, which is just 3. We'll then have 4 plus 3, which is 7, and of course 4 lots of root 3. like so. For question 3, expand and simplify root a plus root b, root a minus root b. Again, I want you to think of this, if you can do, in terms of the difference of two squares. So, to state the difference of two squares generally, we can write it as such. The difference of two squares is where you have one thing plus one thing minus that same thing. That'll always give us a squared minus b squared. And so in our case, what can we think of as being a? What can we think of as being b? Well, actually it's exactly a and exactly b, just in lowercase. And so in our case, our a is like a root a. Our big B takes the form of square root of little b. And so this is going to be root a squared minus root b squared. But root a squared is just a, then minus root b all squared, which is just b itself. We can now use this general algebraic result and apply it to numerical problems like these ones below. And so what we have here below is exactly the same as what we had above. Only thing is the bracket with a minus is written first, but it still works in exactly the same way. So this one here, 12 times 12, sorry, root 12 times root 12 is 12. Minus root 7 times root 7 is going to be just minus 7. So this first one is just simply 12 minus 7, which is 5. This one, root 39 multiplied by root 39 is 39. Then just minus 3, that's going to give us 36. Question 4 reads quite confusingly, but if you take a step back and just think of it in a different way, you'll hopefully see it's actually nowhere near as bad as what you might think. If it stumped you though, don't worry about it. It would possibly stump me if I'm not thinking in the right way. So, what on earth is this number n? How on earth do we work it out? Well, the trick here is to go back to the initial laws of indices and surds and be thinking of root 2 in terms of a power. Root 2 is the same as 2 to the power half. So we've got 2 to the power half to the power n, which is the same as 2 to the power 2 over n. We're told this is a natural number, it's a whole number. And so what this tells us is that this power must be a whole number. And so from this we can conclude, whoops, made a mistake, sorry. Right, half times n, apologies, that's n over 2, not 2 over n. Like I was saying now, we know that this has to be a whole number, and so n over 2 has to be a whole number. And for that to happen, n has to be a multiple of 2. If you take a multiple of 2 and divide it by 2, you still get a whole number. The same thing for this one. The cube root of 5, we can write that as 5 to the power 1/3. So we've got 5 to the power 1/3 all to the power n. Power of a power, so multiply these together. That's the same as 5 to the power of n over 3. So in the same way, we therefore can hopefully see that because n over 3 has to be a whole number, n is a multiple of 3. So it's piecing together. So for example, if n's a multiple of 2 and n's a multiple of 3, what's the lowest common multiple of 2 and 3? So we already know that n has to be a multiple of 6. This one here, using the same idea, the fifth root of 3, that's 3 to the power 1/5. So 3 to the power 1/5 to the power n is the same as saying it's 3 to the power n over 5. Because this is a whole number, n over 5 has to be a whole number. If n over 5 is a whole number, we can therefore deduce that n must be a multiple of 5. So now I've underlined in red, we can use to piece together a picture for what n must be. So just taking all of this here, we need to now realise that n must be some multiple of the lowest common multiple of 2, 3 and 5. And the lowest common multiple of 2, 3 and 5 is 30. So n has to be a multiple of 30. It might be 30 itself, we're going to try it. We are told that n squared is between 1000 and 5000, so let's just try 30. Well, first of all, 30 squared is going to be 900, so n can't be 30, because that's too small. So the next multiple of 30 up from 30 itself is going to be 30 multiplied by 2, which is 60. 60 squared is 3600, and that is between 1000 and 5000. And so we've just shown there that n must be 60. Okay, we're now going to move on to this idea of rationalising the denominator. And so I've got 4 worked examples for you here. So before we do these properly, I just want to talk about and mention what rationalising the denominator is. What it means is, if you've got something in surd form on the denominator, we can remove that surd part. So if it's just a surd on the bottom, for example this one, we can just multiply both top and bottom by that surd. However, if we have something like this, where one term is a surd, the other term isn't, or even, for example, if both are surds, what we do is we multiply both top and bottom of a fraction by what we call the conjugate. So we're going to multiply by the conjugate of the denominator. So what on earth is this conjugate thing? Well, you even will see conjugates when it comes to further maths, but then they're often called complex conjugates. I'm not going to open that tin of worms here, but the conjugate, for example, of these two is just exactly the same thing with the sign changed. So for this one, 2 plus 3, the conjugate of this one would be 2 minus root 3. Just the same thing exactly, but with the sign switched. Over here we had root 7 minus root 2, so the conjugate of this one would be the exact same thing, but with the sign switched. So that minus becomes a plus. And so that's all we mean by conjugate. The conjugates always come in pairs. One's a plus, one's a minus, or one's a minus, the other's a plus, and it just means the sign switched, but apart from that, identical twins. That's what I mean by this word conjugate. So bearing that in mind for parts B and part C, let's crack on and do these worked examples together. So part A, like I previously mentioned, all we need to do for part A is multiply the top and the bottom by root 3. So on the top, we're going to have 1 multiplied by root 3, which is just 3. On the bottom, root 3 times itself just gives us 3. For part B, we're going to take this fraction here, which is 1 on top, 2 plus root 3 on the bottom. We're going to multiply that by the conjugate of 2 plus root 3. So we're going to multiply by 2 minus root 3, both on the top and the bottom. So what that's going to give us, on the top, 1 lot of 2 minus root 3 is just obviously 2 minus root 3. And on the bottom, it's always going to be a case of difference of 2 squares. So 2 plus root 3, 2 minus root 3. That's going to give us 2 times 2, which is 4, then minus root 3 times root 3, which is 3. 4 minus 3 is just going to give us 1. So this over 1 is just the same as saying it's 2 minus root 3. Next up, part C. So we're going to multiply both the top and bottom of this by the conjugate of the denominator. So we've got root 7 minus root 2. The conjugate of root 7 minus root 2 is going to be root 7 plus root 2. And multiply the top by this as well. So now what we're going to have on the top, this times by itself, root 7 plus root 2 all squared, that's going to give us 7 plus 2 lots of root 7 root 2. And finally, plus root 2 all squared, which is just root 2. And on the bottom, we're going to have root 7 squared, which is 7, minus root 2 all squared, which is minus 2. So on the top, we're going to have 7 plus 2, which is 9, and plus 2 lots of root 7 root 2. Root 7 times root 2 is the same as root 14. On the bottom, 7 minus 2, that's just going to become 5, and so that's as simple as we can go. Part D is going to be the same idea. Only trouble with part D is we don't just have 2 terms on the bottom. We've got this bracket squared. So for part D, what we're going to have to do is expand out the denominator. After we've done that, though, it does become exactly the same idea. And so we're going to have 1 over 1 minus root 3. All of that squared. So we're going to have 1 over, well, 1 squared is 1. We double the product, so 1 times minus root 3 is minus root 3. Double that, we get minus 2 lots of root 3. And then minus root 3 multiplied by minus root 3 gives us positive 3. So that's going to give us 1 over, then at the bottom, we're going to have 1 plus 3, which is 4, and then minus 2 lots of root 3. This is now in pretty much the same form as, for example, part B or even part C. So now we can see we can multiply this by the conjugate of 4 minus 2 root 3, which is 4 plus 2 root 3. And also we need to multiply the top by that. So on the top, we're just going to have 4 plus 2 root 3. Whoops. Computer went a bit strange there. As you can see, I never blame myself. I'm too immature. Always blame technology if in doubt. So 4 plus 2 root 3. And on the bottom, again, it's going to be a difference of 2 squares job. So 4 squared is 16. And then minus 2 root 3 times plus 2 root 3. That's going to be minus 2 root 3 all squared. So 2 squared is 4. Root 3 all squared is going to be 3. So 4 times 3, that gives us 16 minus 12, which is obviously 4. So we're going to have 4 plus 2 root 3 on top and 4 on the bottom. Both of these have a common factor of 2. So if we half the top and half the bottom, we're going to get 2 plus root 3 remaining on the top. And on the bottom, half of 4 is going to be 2. And that's question 1 completed. Next is something which might fill you with horror when you first read it. Evaluate the following sum. So you can see there, this looks a bit of a mess. So as a hint, you could use your calculator to get an estimate of your answer, but you'd have to do it by hand to get the exact answer. That's a half-truth. You could, if you had the time and patience, which I certainly don't, type in all of that pattern on your calculator bit by bit. After a good 10 minutes or whatever of double checking you've not mispressed, you would get the answer. But I am not advising you do that for two reasons. A, it's long and boring, and also it's not going to teach you anything in terms of identifying important patterns in maths. So the first thing to think about here is think about the lesson it's in, think about the context. We've been doing rationalising the denominator. That's a big clue. Maybe this is something to do with rationalising the denominator. What I'm going to do first of all is just rewrite this in a slightly expanded out way. So I've included a fraction before the final one here, 1 over root 14 plus root 15. You've got 1 plus 2, root 1 plus root 2, root 2 plus root 3, root 3 plus root 4, and so on. So what's going to be the general pattern here? To make it even easier to spot, you could do it without doing this, but to make the pattern easier in terms of explaining it to you, I'm going to keep the denominators exactly the same, but just switch the order around. So instead of root 1 plus root 2, I'm going to rewrite it as root 2 plus root 1, and so on, like this. Now these denominators, obviously, aren't rational. So what have we done up to now? We've talked about rationalising the denominator. And so with all of these switched over, let's just multiply every single one of these fractions by the conjugate of the denominator. So what we'd do is we'd end up with something like this. So the first one, the conjugate, is root 2 minus root 1. This conjugate, root 3 minus root 2. This one, root 4 minus root 3, and so on. And so if we have a look at multiplying these out at the bottom, difference of two squares again. So this one we'd have 2 minus 1, which is 1. This one we'd have 3 minus 2, which is 1. This one would become 4 minus 3, which is 1. They'd all become exactly 1 on the denominator. So all we'd have left are these numerators. So what we'd have next, as our next step, would be this. Because all the denominators are 1, we can forget the ones and just write it out as just the numerators alone. So we then have this to consider. And is there any sort of pattern? So for example, if we just consider first of all root 2, where else can we see root 2? Well, we can see root 2 here. Only thing is it's a minus root 2. And so this root 2 and this negative root 2 would knock each other out. They'd cancel perfectly. So if I pair these two up, what's going to happen is they cancel off exactly right. So that just becomes nothing. So if you look, 1, 2, 3 away, every 3 steps away is a pairing with the first positive thing. So this positive 3, if you look 3 steps away, it has a negative 3 there. And so next along, each positive thing, 3 steps down the line, pairs up with its negative counterpart and cancels. Same with this positive root 4. That would cancel with somewhere in this middle bit, which we've not included. We don't need to write down all the terms to appreciate the pattern, but this root 4 would cancel with somewhere in the middle. So we can carry this on again and again, just knocking each thing out until we end up with something much simpler. That minus root 14, there'd be a positive root 14 somewhere before this root 15, so that would cancel. This root 15 here, you can see, cancels with this minus root 15 at the end. So an awful lot of things have cancelled. So what I've said here, and what hopefully you can spot, is each positive thing cancels off with its negative counterpart 3 steps to the right. However, sorry, its negative counterpart, 3 steps to the right. So if we have a look at this minus 1, that would have cancelled, if it were to cancel, with something along here. So if you think about minus 1 for a second, that minus 1 would have to cancel with something over here, but there's nothing there. So that minus root 1 can't cancel. Similarly, this root 16, if it were to cancel, it would have cancelled with something down here which doesn't exist. So because there's nothing there to cancel this root 16, that doesn't cancel either. And so after all this pairing up and cancelling off, the only thing we're going to be left with is this root 16 and this negative root 1. Root 16 is obviously 4, root 1 is obviously 1. So after all of that hard, tedious work, actually it just boils down to 4 minus 1. It just becomes simply 3. So that's the trick to working out how to solve this beast of a question. So just be on the lookout for similar sort of tricks. The more tricks you spot, the more time you save, and the more marks ultimately you'll get in your end assessment. So that's me done. Over to you guys. If you could please turn to page 15 of exercise 1F in the Blue Algebra books. Try these parts of question 1, A, C, E and G, and then questions 2, 3 and 4. And that'll give you good grounding and decent practice in the skills we've talked through in this session. So well done, you've got to the end of the first chapter proper. Keep going and you'll be a big success, I'm sure. So thanks for listening, and you'll hear from me again soon. Please be in touch if you get stuck. You know the drill by now. Thank you, and I'll see you again next time.